It is my pleasure to introduce Uwe Bergmann, a physicist here at SLAC, who has a long and distinguished career in X-ray science with many different areas of study, including the investigation of the structure of water, the properties and behavior of photosynthetic proteins. But today's talk is quite dissimilar from both of those areas, and how he got to this point started some years ago, in fact, with a visit to his family, where his mother set aside a popular science magazine in German that she wanted him to look at, and in it there was an article about a famous finding of an ancient text by Archimedes. As it turned out, however, that the Archimedes text had been written over many times, and therefore it was very difficult to read the text that they were most interested in. So Uwe had a brainstorm, and he thought that if the pigments that had been used to write the Archimedes text were distinct from those that were used to write over it, he could use atomic signatures with the X-ray fluorescence to preferentially see the Archimedes text. Many years later, in many successes, he ended up on NPR discussing this work, and someone in the audience out there heard it and thought, I wonder if what worked for Archimedes could work for me. And what working for him meant in this context was investigating fossils, and in particular the fossil of Archaeopteryx. And with that, with Archaeopteryx, that brings us to tonight's topic. And before going on, I'd just like to emphasize for those that are contemplating a career in science, Uwe is not an expert in the classics. He's not a paleontologist, an evolutionary biologist. What he is a scientist who pursues his passion and also is willing to take risks and study new problems, use what he does know to complement what others know. And the reason why I emphasize this is that this is a wonderful aspect of a career in research. You get to pursue your interests. And so I think you will be excited to see Uwe discussing one of his many tonight.
Thank you very much for this extremely kind introduction. I'm honored and pleased to be here tonight to share with you some of the excitement of research going on at SLAC. They glide silently without flapping their wings. They can soar up to very high elevations. They might be as large as a 10-foot wingspan, gliding effortlessly for thousands of miles. Or they might have to flap their wings as fast as 200 times per second to hover close to a plant of the honey they like. They can be as silent that no one can hear them. They can run faster than a horse, standing 9 foot tall. They dive into the water. They dive underwater. They swim. They catch their prey in mid-flight. They catch their prey in the water. They can catch their prey underwater. They can be as bright as a rainbow, or they can be as black as the night, or they might be as white as snow. They have conquered the Earth from the Arctic to the Antarctic, through all regions. They exist now in almost 10,000 species, and they have one thing which distinguishes them more than anything else from any other animal on the planet. They have feathers. Yet, tens of millions of years ago, before these modern birds evolved, there was another creature, a primordial bird, primordial bird is the German for Urvogel, which roamed on the earth. It looked quite different, but it also had feathers. Today's story is the story about this amazing animal, this icon in evolution, and about a new technique, an X-ray technique developed here at SLAC in order to try to bring out any information which might be hidden in the very few fossils we can find about this animal. The story I'm going to tell started with a letter from the German scientist Hermann von Meyer, to a journal which today would be equivalent to writing a letter to the journal Nature, for example. On August 15, 1861, Hermann von Meyer, from the lithographic shale in Solnhofen, Bavaria, I was informed about the slab and counterslab of a fossil which with great clarity can be evidenced as a feather that is not distinguishable from bird feathers. In the very well-known organization of pterodactyls, pterodactyls are flying dinosaurs, there is nothing known that could be concluded as a plumage. This would therefore be the remains of a bird of the pre-tertiary. See that he used the word bird in this first letter to this journal. This is the journal New Yearbook for Mineralogy and Geognosy. Now, this is what Hermann von Meyer had been heard about. This is the original view of the fossil, and this is one of his very first hand drawing of it. The reason why he said that it is not distinguishable from a feather, from a bird feather, can be seen here by just showing the comparison to a modern blackbird feather. There is really nothing which distinguishes those. What was a shock at the time was the fact that in the limestone of Solnhofen, a small town in Bavaria, which was known for its many fossils of the Jurassic time. For example, you can see geckos, there were freshwater crocodiles, there were even some rare fossils of flying dinosaurs, and some salamander-like predecessors of modern reptiles. In that area, it was assumed that was well before the time of any birth. Hence, when he reported on that find, there was a big surprise and there was almost a sensation and even a large disbelief from his colleagues. Then, less than 6 weeks later, he followed with a second letter to the same journal. Following my letter from August 15, I can now report that I have studied the feather from Solnhofen in detail and came to the conclusion that this is a true fossilization of the lithographic shale, and in complete agreement with a bird feather. At the same time, I have received news from Mr. Justice Councillor Witte that an almost complete skeleton of an animal covered with feathers was found. Comparing to living birds, it shows some differences. I will publish the feather that I studied with an exact drawing. We just saw that drawing. For the description of the animal, I suggest the name Archaeopteryx lithographica. The name he chose means ancient feather. The fossil he found, this is the first depiction of the fossil, was clearly indications of feathers. You can see the imprints here, but it also had features which were unusual for birds. It had a very long tail. Birds don't have a very long tail, and it had also, and this is not so seen not so well, I'll show you that in a second, it also had other significant differences, including a beak with teeth. Now, the story of the first Archaeopteryx specimen in itself could cover many lectures. There is literature about it. It ended up being sold to London, and it is now the top fossil in the London Museum of Natural History. It was a big blow to the German academic community because they really had hoped to be the ones to own that fossil. The owner was so paranoid that he actually wanted to make money with it, that he showed it to bidders only for a short time, and they couldn't take any images, and they had to go out again. However, one of the German paleontologists, he actually remembered the fossil and made this drawing out of his memory. You can see he drew it in mirror, but it was actually an amazingly good replica of the original fossil. The first published drawing of the fossil looked like this, and it immediately stirred up a very large debate. Now, you have to understand, at the time of 1861, we are speaking about just 2 years, less than 2 years, after Charles Darwin had published The Origin of Species, a work which was, even in the paleontology community, incredibly controversial. Most of the top paleontologists in Europe were convinced that there were archetypes. In other words, creations, creatures which do not change over time, which do not evolve. And they were one of the big criticisms of Darwin's theory of evolution, namely that one species can actually, with long enough time, turn into another species, was always, they always said, show me some transitional fossils. Show me a dinosaur turning into a bird. Show me a crocodile turning into something else. And obviously, when this fossil came out, the supporters, the very few supporters of Darwin, they said, look, here we have something. We have feathers, and we have clearly the features of a dinosaur. Let me just show you in the second fossil which was found. This is the Berlin Archaeopteryx, and you can see it again. It has a very long tail. Here's the beak. Now, from a different fossil, you can see a scanning electron microscope. This is the beak. Clearly with teeth, and then there's also, it had claws. At the end, it had claws, and all of those features were not known at all in modern birds. So, given its look and given its time of finding, the Archaeopteryx has remained one of the most iconic fossils there is, and it is used in every textbook as one of the prime examples of evolution. Now, today, the interest in the Archaeopteryx is not to prove or disprove evolution. There are many other reasons why the Archaeopteryx is still studied. Amongst them is the question of how did feathers evolve? How did the flight start? There's also a debate whether the Archaeopteryx is actually the ancestor of all birds, or whether it was in a side branch. But if it was part of a side branch, it is still, however, would be still extremely close to the ancestor of all birds. This is a model of a reconstruction of the bones, which shows you the skeleton of the Archaeopteryx. Again, as compared to modern birds, rather large differences. You see the long tail, and you see the teeth, and there are many other differences. Now, if you are interested in the history, in this amazing history of the early finds of the Archaeopteryx, you should look at a book. Before I show you that book, I just want to give you, tell you about how rare the Archaeopteryx fossils actually are. So far, there have only been 10 fossils plus the original feather were found. This is how they look like, and next to them is the location where they are currently located. An 11th fossil has just been found last year, and that was actually big news for the community. And if you look at these different fossils, they are differently well preserved, and it depended a little bit on probably how the birds died, or even more importantly, how long they floated. It is assumed that they dropped in a tropical lagoon where they lived, and then they sank to the ground, and there's the question of how long they floated before they sank down. Generally, the ones which died closer to what was the shore at the time are better preserved, and the two best preserved are considered the Berlin Archaeopteryx, and then the only other specimen, which actually it's the only specimen which has left Europe, the Thermopolis Archaeopteryx, which is now located in the Dinosaur Center in Thermopolis, Wyoming. If you want to know a little bit more about, if you want to read, it's a $12 paperback. I can recommend it, from Paul Chambers. It's called Bones of Contention, the Archaeopteryx Scandals, and it tells you how the Archaeopteryx was used at the time when it was found by both supporters of Darwin, misused in fact. Supporters of Darwin also misused it, and certainly a lot of creationists and those who didn't believe at all that there could be an evolution, they found many reasons to dismiss it. In fact, one of the most famous German paleontologists at the time, of the name Wagner, his theory was that there was a creation. Now, you have to keep in mind, these are people who have seen many, many different fossils. They have seen fossils of animals which are clearly no longer on the Earth. But the thought, for example, the theory, if you want to call it theory, it's not really a theory, but the thought was that, oh, there is a creation, and then everything dies, and then there's a new creation, and then everything dies, and then there's a new creation, and then the biblical creation is just the last round of creations, and everything before then always completely died. And when he was confronted with this fossil, they said, so what do you say? This is clearly a dinosaur, and it has bird-like features. This looks very much like a transition. He just said, no, it's just a dinosaur with feathers. It's nothing like a transitional fossil. Very simple. Now, this is where the Archaeopteryx, actually, this is the Earth 150 million years ago during the time of the late Jurassic. And you can see some major differences to how it looks now. What is now South America and Africa were still together. North America was not really separated, and then Antarctica and Oceania, like Australia, were still together. And the place where the Archaeopteryx was found was in this region here, and it was, at the time, it was a subtropical lagoon area. There were small islands, and there was water, very low water. And the interesting thing is, because the Archaeopteryx is now found in Bavaria, and Bavaria is at the 49th latitude. So that's about that's the border between US and Canada, actually. And when people say that was a subtropical lagoon, then everyone says, how is that possible? That doesn't sound too subtropical when you're in Bavaria going skiing. And the answer is, 150 million years ago, the area, which is now Bavaria, was actually between 20 and 25. So it was in a region much further south, and over the 150 million years, it actually drifted to the north, like all the other continents also drifted very large distances. Here's a depiction of the area where this is a painting from a painter from the time, inspired by scientific evidence, where the Archaeopteryx might have lived. It is not, as you can see, it's a rather dry landscape, and the fossils which were found didn't die in that landscape. Those were birds which had flown over the water onto those lagoons, and then the thought is they might have been caught for whatever reasons. Maybe the eastern winds were getting too strong, and then they just basically died over the water. They sank into the water immediately, relatively fast, with low oxygen, so there was not much of degradation. And then over the time when the sediment of the limestone settled in and the whole ocean basically dried up, they were conserved in that area. Now, I'll give you a little bit more of the anatomy of the Archaeopteryx. This is a comparison that tells you the size and also the shape. This bird is called Pika Pika. Who knows what it is? When I first read it, I think Pika Pika stands for it steals things. And in fact, it is the European magpie, which the Latin name is Pika Pika. And that's about the size of the Archaeopteryx. And again, if you look at it, rather different form of the wings, and then also the longer tail. Keep in mind that the magpie has very long tail feathers, actually much longer than the bones. And now here's another image, and I like that very much because it gives you an idea. This is a called Bambi Raptor. It's a theropod dinosaur. It is considered one of the so-called feathered dinosaurs, and it is very closely related it's one of the dinosaurs which are probably rather closely related to later birds. And you can still see that even from that animal, if you just look at the change of the skull, and then you have the Archaeopteryx in comparison, and then you have a modern chicken, basically. Now, the important thing is that over time, as soon as these animals had evolved for flying, their bodies started to change to optimize, of course, for the flight. And there was no need to have a long kind of flexible spine. That didn't really help you that much. You wanted to develop your muscles all in this breast region, and so they started to really tighten up, and they started to get tighter, and also that tail, that's weight. You don't really need that extra weight, and so you can see really about how that transition is, and all it takes is that the first time you take off and you find some advantage of being in the air, you have a larger range, etc., and then everything sets in, and slowly it advances. I would rather take questions at the end if you don't mind. Now, this is a quote from one of the evolutionary biologists reminding us about the iconic nature of the Archaeopteryx. Nothing can challenge the Archaeopteryx as historically, scientifically, politically, and aesthetically the most important fossil bird ever discovered. I should point out there was, in 1995, the Archaeopteryx fan community was in a small crisis, because in the region of Liaoning, China, they had found a bird which had also feathers like the Archaeopteryx, and which also had claws like the Archaeopteryx, and which also had, it didn't have teeth, but it had like a horned bill, and it had lots of theropod features as well. And at the time, the dating wasn't done properly, and someone said, oh, the Archaeopteryx is dethroned. We have found a bird which is older than the Archaeopteryx. And the name of this bird is Confuciusornis sanctus, and it turned out that they were actually wrong, because that Confuciusornis is from an area which has been then radiocarbon dated to about 122 million years old. It is a very, very important fossil, and they have found many of those now, and it is possible, and we don't know yet, that many more fossils are needed to find it out, that this bird might actually be closer related to the true ancestor of the birds, and then the Archaeopteryx might have been a side branch. These are discussions which are ongoing right now, and it is also important to note that in the same area where the Confuciusornis sanctus was found, they found so-called feathered dinosaurs, which didn't have the features and didn't have the capability of flight, but which had feathers. And in fact, it is pretty clear today that feathers definitely did not evolve for flight. They evolved for other reasons, and there are different theories about that, but the flight was a byproduct which came much later. Now, I'm going to show you a couple of more depictions of the Archaeopteryx, just to show you how little we really know about the plumage and the feathers. This is the model at Oxford University Museum. It looks quite different than the first one I showed you of the Urvogel. They came up with black and white and all kinds of colors. No one really knows. No one has found any material even from the original feathers. All which is seen in these fossils are imprints which are left over. There's some bone material left over, but no one thinks or thought until recently that there is actually any real material from the feathers, leave alone any information about the colors. Here's another one. Again, you can enjoy all these colors. It's sheer fantasy. Really, no one knows. These claws, by the way, were thought so some people think that the Archaeopteryx actually landed on a tree and then that was hovering maybe on the tree and then climbed down. But again, that is also one of those controversial theories which you don't know until you find more fossils. However, Some also are careful, and this is a model of the Archaeopteryx, and the person who made it, in particular, avoided to put any colors on it. They said, you know what, we really don't know the colors, so just let's leave the colors off. I think it's a very beautiful depiction of the Urvogel. Now, that was exactly the situation for us when, as Kelly just pointed out, the famous fossil hunter Pete Larson from the Black Hills Institute in South Dakota heard on NPR News about this new imaging technique. And he called a colleague of mine, Bob Morton, who is part of the Archimedes project, and who already had talked to me about trying to use synchrotron radiation to look at some fossils, because he had done some work on the conversion system, which was very slow years earlier. And so Pete Larson, he's actually the one who discovered the T-Rex zoo. He called my colleague, and then we ended up writing a proposal to the SSRL Proposal Review Committee, that's SSRL is the synchrotron here, to request for beam time to measure the Archaeopteryx. Pete Larson knows people, and he's very well known in the community, and he can get, if there's any fossil, he can get it for you. And he knew the person who owns the, he knows the person who owns the Thermopolis Archaeopteryx, is an industrialist from Germany, and it's on loan in there, and he said, no problem, we can get it. I'll just show it to you one more time. This is the view of the Thermopolis Archaeopteryx, and this is kind of the visual image, and you can guess just a little bit anatomy, can guess some of the teeth. So what at the time, so being scientists, you know, being interested in things, we were asking ourselves the question, what do we still have to learn about these fossils? So keep in mind, almost everything which is used to discuss fossils and also the role of fossils in evolution is based on the visual inspection of the fossils themselves. And the question we ask ourselves, is there anything more in the fossil that you can see by eye? And so, for example, is there a chemical fossil? Is there some chemistry left of the original animal which has been preserved over 150 million years and has not been eaten up by bacteria or washed out by other things? What can we learn about the chemistry of the fossilized animal in comparison with related existing species? Can we find something and then check it with other fossils and with also modern birds to learn something about what the real chemistry was? And can we learn something about the fossilization process? One of the difficulties with any fossil is you always want to know what was original and what came later, and then how came it later? How did it come later? And to answer these questions, you need a geochemist, really, who is an expert on transport mechanisms, and he knows how chemicals move around and what is likely to dissolve. And that's where Roy Vogelius and his team from Manchester University actually joined efforts with us. And then, of course, the big question, can we reveal soft tissue? Can we reveal traces of the feathers? And even, can we even dream about finding something out about the color, maybe, and the type of the feathers? So, Wilhelm Conrad Röntgen, he was 15 years old when the Archaeopteryx fossil was found, and he made what is probably one of the most famous discovery of all times, namely that you can use X-rays to shine through material, and here you see his first X-ray image. Now, X-rays is a powerful tool for several reasons. It is powerful because, first of all, you can shine through things in some cases, but it has another property. It is also a very powerful analytical tool because it can detect different elements. X-rays are sensitive to different elements, and I explain to you how that is. If you look at a cartoon model of the inside of an atom, you will see, and this is not to scale, you will see a nucleus which is positively charged, and then you see electrons in different orbits going around the nucleus. Now, the charge of the nucleus balances the number of electrons. So if you have an iron atom, you have 26 protons, so you have a charge of plus 26, and they are surrounded by 26 electrons, and they balance each other to be neutral. And what it means is, as you know, positive and negative attract each other. What it means is that all of these electrons are bound by this attractive force to the nucleus, depending on how close they orbit the nucleus. The ones which are very close on the inside are stronger bound. The ones which are close on the, closer to the outside in the valence orbitals, they are loosely bound. What X-rays can do, X-rays have enough energy, unlike most other, unlike visible light, even UV light, etc., that they have enough energy to knock out these electrons. And what they also do, every once in a while, that when they knock out an electron, that hole is immediately filled and sends out what is called a fluorescence X-ray. And the process looks something like this. You have the X-ray coming in, knocking out an electron. There's a hole, and that hole is quickly filled from an outer shell, sending out a secondary X-ray. This X-ray is called the fluorescence X-ray. And the color, and I use the word color in quotation marks because X-rays don't have color, they are invisible. The frequency, the wavelength of this X-ray tells you exactly about the difference of the orbit of this electron and this electron. And because every element in the periodic table has a different nucleus, so they have a different bonding energy, they have a different fluorescence. So if you have an energetic X-ray, enough energy to knock out an electron, your atom will send you out a particular signal which is unique to that atom. If you have a lighter one, it'll send you out a different wavelength. If you have a heavier one, it'll send you out a different wavelength again. So you have a very powerful tool to actually, if you shine X-rays on a piece of material, for example, you could shine it on the Archaeopteryx. What you will see is, and this is again, it's an animation, you will see that X-rays will fluoresce out, and these X-rays will have different colors depending on all the different chemical elements which are in this case, in the fossil. Now, I was told there is a public lecture in 2 months which will bring to question the following statement. All life needs 6 elements. Hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. So hydrogen, carbon, nitrogen, oxygen, so this makes water, phosphorus, and sulfur. And we might learn in a couple of months that maybe we don't really need phosphorus, but as of now, let's just assume we need also phosphorus. In addition, so these are very important elements. So I just pointed out carbon, nitrogen, oxygen, and phosphorus and sulfur. In addition, we have in our bodies many, many different trace elements, and they're also very important for our health. We have low levels of iron. Of course, we have high levels of iron in our blood, but we have also levels of iron pretty much everywhere. Cobalt maybe rarer, but also copper. Copper we have, for example, in our pigments, and zinc is also part of our diet. It's in the bones, and we have, of course, many other elements. With the technique, with the X-ray fluorescence technique, you can access many of those elements, but not all of them. It is very difficult to get the first 2 rows. It's very difficult to get those. In fact, if we wanted to get anything up to neon, so I'm showing the first 2 rows. If we wanted to get anything up to neon, we would have to put our Archaeopteryx specimen inside a vacuum chamber, because these X-rays are so soft. They really come only from the surface, and they are immediately absorbed in the air. However, we can make a setup where we can get access to this second row. So aluminum, silicon, phosphorus, sulfur, chlorine, argon. Of course, we have to be careful. That's in the air. And then clearly all these other elements. Now, when you do a chemical analysis of a fossil, you can say, oh, someone says, oh, no problem, I'll give you a piece of the fossil, you put it in your X-ray beam, and you measure all the elements. And then you say, no, I don't want that. I want to see the whole image. I don't want just one piece. How do I know that that piece is really from the area which I like? And so before I show you how this works, I'll just show you a typical X-ray fluorescence spectrum. This is, it's very straightforward. You have energy here, or wavelength, and you get different peaks. And this is actually a spectrum which was taken from the Thermopolis Archaeopteryx. And you can then, with your detector, you have your little orange book, and you can look up what the energies are. So 4 kilo electron volt, that's the unit. You have calcium, and then you have iron, etc., etc. Each of those peaks corresponds to a different element, and you can actually set a window in your detector which just collects this element, and that's how you can detect this element. And you have, for example, zinc, and you have, for example, lead. And what the technique we want to use, because as I pointed out, we don't just want to do it for one element, but we want to do it for the whole. Let me just see whether I can find my cursor here. Yeah. Need to wait for a second. So what we want to do is we want to take a very small beam and then take at any spot. Now we get the full spectrum. We get a full chemical analysis. But now we want to do it everywhere. So what we do is we actually scan this beam across one line. Oh, I can do it better with my like this. So we scan it across and then move it up by 1 bit, and then scan it across and move it up by 1 bit. So basically, we have the stage moving back and forth, and we take a whole analysis on each little spot where the beam hits the sample, the specimen. And in order to really get the whole image with high resolution, we have to do that about more than 10 million times, because we want to get a 10 megapixel image of the fossil, right? It's not that different than your iPhone camera right now. And so you can imagine that in order to do that successfully, we cannot do it. We cannot wait for a second to get each of those measurements, because that would take us half a year. We have to do it fast. So we have to come up with a system which can, in milliseconds, actually read out all this information, all the spectral information, and then store it into an image. And that is really the technique of what we call the rapid scan X-ray fluorescence imaging, and that's what we have developed here. And now we have a size of the length of the whole specimen. We do that in about 15 seconds, and it takes us maybe 28 hours to do a full scan of the Archaeopteryx, and we did it at 2 different energies. So basically, it's not such a long experiment. And where do we get these powerful X-rays? Because you can imagine, if you only measure for a millisecond or 3 milliseconds, in order to get any signal, you need a very strong beam. You know where we are. We are in Panofsky right here. This is the LINAC, the famous LINAC, and this is in the research yard down here is the Stanford synchrotron radiation light source. It is one of the most powerful synchrotron sources in the world. It is, however, not as powerful as our new X-ray laser, just FYI. It has about 25 experimental stations. This is the schematic, and scientists from all over the world are, as we speak right now, conducting experiments at these different stations. The experiment we have proposed uses one of them, and here are some images now. This is the truck arriving from Thermopolis, Wyoming. They didn't want to fly. They took it by truck. And we have here our colleagues starting to prepare the fossil. You can see it here, sitting on this very sophisticated wooden box. You can probably recognize the fossil hunters on their outfit. And what we did is, in order to protect it, we put like a very thin wrap of cellophane on top of it. Here you see now the fossil hunters, because they are the ones who get blamed if they drop it. It was valued at $6 million, and I was happy that I didn't have to handle it. And here is a view of our experimental setup from the top. You can see the X-ray beam is coming in through here, and it goes actually through a very, very small pinhole, and the pinhole is about the size of your hair and determines actually how large the X-ray beam is, how good the resolution of this big image we're going to get really is. And then here you can see the detector looking at the side. This is the fluorescence detector. One of the other things which makes fluorescence so powerful is the following, that if you don't have an element on this particular energy in there, you're not going to get a signal, because all the scattered light has the wrong energy. Your detector is not going to see it. It really has a much, much higher sensitivity than your normal dental X-ray, where most of the light just goes through. I like the comparison to say that, think about the stars. You would never look at the stars during the day, even though they shine as bright, because you have this huge background which makes it basically impossible to even detect them. But if you can turn that background off, you can see even very faint stars very nicely. And this fluorescence technique, as compared to your normal chest or dental X-ray, actually has a sensitivity which shows the same comparison. And now I'm going to show you one more image of the setup. This is now the Archaeopteryx. We scanned it upside down for various reasons, but I'm going to show you the images in the right way. And we are going to look now at some X-ray images, and I'm asking to dim the place for that. So again, remind you, this is the physiology. And I have to say one thing. When we put this sample in, when we put the specimen in, we really had no idea what's going to come out. It is one of those things, you just put it in and you look and you don't know what you expect. So let me start and let's look together at some X-ray images. The first image I want to show you is on the element manganese. And you can see very strong that there are these bright little, they look like little dendrites. And they turn out to be inorganic precipitates called pyrolusite. And they are very typical for limestone. So as pretty as they look, they really don't tell us much about the Archaeopteryx. In fact, if you look at all the bones and everything, there's hardly any manganese in there. You can see some features. There's maybe a little bit of shading going on. Keep in mind, these X-rays, when the X-ray beam hits and there's some indentation, some of the fluorescence might not come out. But in terms of the content, there's really very little manganese in there. Now, the second image, which I show you, is on bromine. And there we found our first little surprise. You have some areas here and here in the bone, and then another area here and here in the bone, which look very different. And what it turned out, that they are actually not part of the Archaeopteryx fossil. They are curation effects which were put in much later. Someone wanted to make this fossil look a little bit nicer, so the missing bone, they just plastered it up. And I want you to keep these places in mind here. So remember, when you look at the next images, in the coming images, think about this place and then this place here. In some of the images which are going to come on later, you will not see them because that is material which is really in the bone and was actually absent. So synthetic film, curation effect, artifacts, nothing really new and exciting. Next one, chloride. Again, the other information which I want you to have is, if you see something whiter or brighter, that means there is more of it. If you see something darker, it means there is less of it. Now, again, very little chlorine preserved in the original fossil. However, we have a couple of things here, and guess what this is? These are big fat fingerprints from people who just couldn't resist on putting their thumb or their hand on the fossil, and it's just the little amount of sweat and salt you have on your hands which is going to be there. Now, as uninteresting they are for the fossil, they tell you one thing. They tell you that this technique is really incredibly sensitive. if you can make out just a tiny bit of material which was left over by an uncareful handling of the fossil, that means whatever you see, you can see very small concentrations. In fact, we have measured it, and I will discuss that. You can see down to a few parts per million of elements which are still preserved. Now we went to copper, and here we felt that we had our first little success, because what you see here is you can see that clearly there is more copper signal in the bone area than around. And we checked it, so we did some point analysis. The levels are relatively low, but they're not completely out of range of some of the copper which might also be preserved in a live animal. So we think, also knowing the chemistry, the fossilization chemistry, that these copper signals were really part of the original animal from the bone. And then, even more important, we also found zinc. And the signal here is very, very weak. But you can clearly see, again, like you can see here, this is missing here, there's nothing here, and this is also weaker. But you can see that there is an enhanced signal to everywhere where the bone is. You can also see, you can see these stripes on the image, and you can see this ugly little thing here. And what happened is that our cellophane, which we put around to protect actually the specimen, ended up having some traces of zinc material in it, and it just showed up. And at one point, because we were not careful, we made a little dent or a little hole into this cellophane, and that showed up because it just had crumbled up, and then all of a sudden you get a larger signal. But even though that might not sound very, even though that might not look as very convincing, if you go through the analysis, so we went then to several spots, for example here and at the bone, where we did a careful analysis of how much zinc is actually in there, we found that as compared, like a modern seagull have about 100 parts per million of zinc in their bones if they are a healthy bird. And what we discovered is that the Archaeopteryx has in the skull of order 50 parts per million of zinc. There is also some residual zinc in the stone, but something of order 30 to 50 parts per million. So not unlike modern birds, and also the copper levels, very similar analysis, a little bit lower, not unlike modern birds. Now I have to say something about when you find a chemical element in a fossil. If you find nothing, that's sad. If you find something, that's good news. But if you find too much, that's bad news again. Because if you find too much, you know it cannot be part of the original bird. You know it must have come less. So what you do is you look at the levels, you analyze the levels, and then you think about the transportation mechanism, and then you come up with your best guess whether that's original or whether that came later. We are convinced that these transition metals, these trace elements, were originally in the bone and giving us the indication of a healthy bird at the time. What we did not find is any trace metals in the feathers, because we were hoping that the feathers had maybe something left and were not just imprints, as anyone is thinking or has thought to the time. Maybe they had some, maybe we could find something, but unfortunately in this fossil we couldn't find any trace metals. In particular, copper is very important. We couldn't see that. If you look at the image, you will see there's nothing really left. So there was phosphorus and sulfur left. And let me now go really straight into the zoom in a little bit into the area. Again, so here's the fossil. I'm going to zoom into this area. This is an area where you can have mostly feathers. And you can see in the original fossil there are some imprints, sporadic imprints, but it is really impossible to say whether that's anything just stone. And so this is now our phosphorus image, which came out, and this was our first big surprise. What we actually discovered is that indeed phosphorus from the original bird has been conserved on these feather shafts. So the shafts of the feathers had the slightest trace of phosphorus had left in the fossil. And this was really, it is really completely unpredictable. If you look at this image, it would be unpredictable whether you should look up here or up here or up here, or maybe here. Only when you look at the X-ray image, you can actually make this correlation. So this was, we were really very excited about this. You can also see here a very beautiful image of the teeth in the skull. And then if you go to the other side of the fossil, so you go into this area, again, you can see now some of those manganese precipitations. And then here, you have, these are actually traces of iron rich, and you can see imprints, but you would never guess that there's anything else in there. But if you look at the X-ray image, you see that, in fact, there are remains of the original feather shaft have been preserved over the 150 million years since this bird died. In addition, we looked at the phosphorus. So this is now the full phosphorus signal of the whole object. And besides, of course, these shafts, which are really, this was really our great moment of joy. Again, look at the curation. These ones certainly didn't have any phosphorus in their curation material. Finally, sulfur gave us almost the identical image than the phosphorus, but somewhat weaker. So the elements of the sulfur elements were less preserved in this bird. I can zoom in again into these two areas. Here you can see on this side you can see very little. You can see a little bit of a feather shaft and like some very small hints. And on this side, on the other side, you can see just one little feather shaft. So both phosphorus and sulfur are key components of the feathers. In fact, some people think that the evolution of feathers was accelerated by the fact that sulfur is, if you eat very protein-rich diet, you have a lot of sulfur-rich amino acids, and in order to get rid, that your body can get rid of those sulfur, maybe the molting of birds and maybe the evolution of feathers was actually driven by that need. And so we were really excited that we had now discovered the original soft tissue chemistry which has survived but is not visible to the eye. Now, in conclusion, we found that Archaeopteryx bone chemistry was very similar to modern birds. Feather chemistry can be resolved for the first time, despite the fact that many people, there are probably thousands of papers on the Archaeopteryx, have studied this for over 150 years. And we also find, and I have to say this is really just the very first baby step, that this technique where you take an analytical image of a full big fossil is really a very powerful tool. And let me just show you a couple of images on other fossils which we have done since and partly also before. This is from a paper published 2 years, actually this was published last year. This is a fossilized squid from Hakel, Lebanon. Squids and even octopi are very important because the fossil record is very poor. In fact, octopi, only 12 fossilized octopi have ever been found because they have mostly soft tissue and they often don't leave much of an imprint. So I'm not allowed, the octopus is still embargoed, but I can show you some of the images from the fossilized squid. Here you can see the tentacles coming out clearly, and if you zoom in more, you can find even some stomach contents and some details, and they're just elements, different metals, which are preserved. This is from Pete Larson. He likes dinosaurs, and so we took some X-ray false color. These are also X-ray fluorescence images of dinosaur skin, and what you can see is actually that what you see in the chemical image is different than what you see from the imprint. So you can not just take the imprint and say, oh, I know everything about the skin. You look at the X-ray image and you see more features. And then a friend and colleague of ours, Bruce Leake, came by, and he loves birds, and he has lots of bird feathers, because at the end, what we really are after is we would like to learn something about the coloration and about the shades and the different chemicals which are in the feathers. And he brought us some beautiful feathers, and I'll just show you some X-ray false color images of these feathers. And I'm not going to even tell you which elements they are, but you should remember that these are, each of this color represents a different chemical element. These are all metals, and you can see there's clearly a correlation. For example, look at this one here. You have some dark shading here, and there's clearly a correlation of feathers with trace metals. And there's another interesting effect in this feather, which looks completely white to the eye. If you look at the X-ray image, you can see some banding here. Because the chemistry which originally was in that feather actually indicates that there is still some banding in here. And so I would like to conclude my talk. I have the reference of this work, which I mostly discussed today. We have a copy. We have about 50 copies outside, and also the supporting material. If you are interested, you can take yourself a copy. We also have some posters for if you have young children or some people who like. We have some posters of X-ray, of the X-ray fluorescence image of the Archaeopteryx, and you can take one. There is an article in New Scientist which is coming out this week called "Blood from a Stone," which is featuring this work. I should acknowledge Peter Wellenhofer. He wrote an incredible book about the Archaeopteryx. This is the German version which I got as a gift from my friends, and it now also came out in the English version. You can find it on Amazon, for example, and it has lots of detailed material about all the different fossils and about the Archaeopteryx. And there will be a 6-part National Geographic special highlighting this work. The starting date in Europe and Australia is February 6th. The starting date in the United States will be sometimes in the fall. So they don't. I think it's 160 countries, but they don't start at the same time overall. But keep your ears open. Sometime in the fall there will be a series on where they describe all new techniques to look at fossils. And I should also point out that in December we got the counter slab to the Berlin Archaeopteryx. That was absolutely amazing, and I cannot show you the images yet because they're still embargoed. We also not just got the counter slab, we also got the original feather. It's a tiny little feather, and all I can tell you, in this feather we have seen more chemistry, more of the metals than in the Thermopolis. But that's as much as I'm actually allowed to tell you. And we have also worked, I mentioned before, the famous lining birds. This is the Confuciusornis sanctus, and this one, again, we have some evidence of some patterns in the feathers, and that on the other hand, that paper will be submitted within the next 2 weeks. So that is really ready to go. I would like to acknowledge my colleagues, in particular the group from Manchester, Roy Vogelius. He did really most of the work. Phil Manning. I give you some characterization of these people. Bill Sellers. And then Holly and Nick. Those are the graduate students. They really never rest. Pete Larson and Sam Farrar, fossil hunter, deputy fossil hunter. And then last but not least, Bob Morton, who originally suggested to do fossils, and his colleague and friend Ken Huntley. I'm also grateful to an incredible support by SLAC, and here are the people in particular I would like to mention, and there were many, I have to say, Martin George and Alex Garachenko, who came up with this rapid scanning mechanism with the software and the hardware to really start to do these scans. The X-ray team, Dave Day, Bart Johnson, J.R. Troxel, Tom Hosteller, Tom Rabideau, Jeff Maskey, in minutes he machines you something if you need it for the samples. The detector group, Matthew, Allison, and Eric. Andy Prado for electrical power, which we almost need. And then Brad Plummer, who is here, and Kellen, they really helped me. And the whole communications team actually really helped me with this presentation. I'm happy to take some questions. And in the background, I will just leave you with some snapshots during the work on the Berlin Archaeopteryx. Thank you very much.
Before we begin with questions, are all of the microphone runners, do they have microphones? At least we have two. Okay, so when you raise your hand to ask a question, that's great, but wait for the microphone, and we'll be patient with you. So there's a woman in the back who's ready for a question next to you, Sam.
Can you hear me? Can you hear me?
Yes.
Okay. So I have a few questions, but my first question is, if you were to take an image X-ray of the opposite side of the bird, do you think you'd get a different image and different result? In other words, have you ever thought about cutting back the other side to see what it looks like? The second question is, you're assuming that we're going from land animal to flying animal. Have you ever thought that it was the reverse? Flying animal to land animal, or flying animal to swimming animal, or swimming animal to flying animal to land animal? And then the other question is, you showed two different birds. You showed the magpie compared to the other one, and the different wings were shaped a little different, so the aerodynamics are different. Has anyone studied what the aerodynamic or flying patterns would be based upon the shapes of the wings? And then the fourth question I have, and my last question, my very last question, I promise you, is that you'd mentioned that because Bulgaria moved. That was the country, right? It moved.
Bavaria.
Bavaria.
Yes.
Sorry.
Yes.
It moved, and so at one point it was in a warmer place.
Yes.
So have you ever thought? Has anyone studied whether or not, based upon those movements of the Earth, it would tell you historically what the next phase in evolution would be based upon those movements? That's all.
Thank you. Well, I can easily start with the last question. It's very well known that Australia, which was we know pretty much when it was cut off, has unique fauna. Like all the marsupials, and there's an example how when you have continental movements, how separation starts to play a role into evolution. Right? It was only when humans actually settled in Australia that they brought in rabbits and they declined. So they had a very special fauna, and the same is true for anything. Now, with regards to the evolution of flight. I actually like that question very much, and I have a quick slide on this. First of all, I should point out that that there are three different independent mechanisms how flight has evolved in big animals. Now, there are many other mechanisms how flight has evolved in insects, but for the big animals, there was basically the birds who started to fly. There was basically some of the mammals, like the bats, and there was also independently the dinosaurs. So flight is really not unique to birds, and it's also not even associated to birds, as you know, from penguins and ostriches, etc. So the thought how flight evolved in birds, there's two competing theories. One of them is shown here on the top. This is that feathered dinosaurs started to climb on trees, and then basically a little bit like a flying squirrel jumped off, and then as those feathers got longer, they could go larger and larger distances. So this is the tree climbing theory. And the other theory is that feathers actually evolved well before dinosaurs started to fly, and we know that is true because Archaeopteryx, who has very much dinosaur-like features, has completely modernly evolved feathers. Right? So Archaeopteryx is certainly not the fossil which started the evolution on feathers, but it's a fossil which could fly. We know that also. And so some of the theories is that basically maybe they first jumped and then jumped longer distances. Some people make even calculations if they run, what speed they need in order to get a running start for flight. It's an unknown question. It's not answered until today, and we need more fossils in order to address this question. And you mentioned, what was the other question you mentioned? The counterplate, yes. So that's a very good question. The Thermopolis Archaeopteryx, we don't have the counterplate. It was never found, or if it was found, it is somewhere and we don't know where it is. Typically, when you splice open a plate, it's a little bit a question of luck how it comes out. Let me take the London Archaeopteryx as an example. The London Archaeopteryx, actually no, let's take the Berlin Archaeopteryx. The Berlin Archaeopteryx looks beautiful, the skeleton looks beautiful on the main slab. The feathers look better preserved on the counter slab. And that's why we actually try to get the counter slab, and we got the counter slab. We also wouldn't have gotten the main one. But anyway, so when you open up the fossil, you look and you can get a first visual idea which side is better preserved. In the feather, which we did get, we got the counter slab, which is in Berlin. The original, what is called the main slab, is sitting in Munich. And if you look at the two, I actually even have a photo of that. The counter slab seems to be more interesting because it has a darker coloration which is left, right? And so it's a very good question, and I think that ideally you would like to measure both. In reality, you choose whatever question you want to answer, and that's which slab you take if you have the choice.
Can you tell us more detail about why you had to use the synchrotron, what energy levels you needed to get this image, and would you benefit from even higher energy or intensity levels than the beam you currently have?
Yeah, thanks. That's an excellent question. And so there are two aspects to doing this X-ray fluorescence imaging. One of the aspects, I'll just wait for this. One of the aspects is what is the energy? So by energy, it is really the wavelength, the frequency you want to use to excite whatever level you want to excite. And sorry, I'm distracted here. So let's just leave it like that. So it is, if you're interested in transition metals, or if you're interested in phosphorus and sulfur, you use a lower energy for excitation. If you're interested in very heavy metals, you typically use a higher energy. But the good thing is that even metals as heavy as lead have some fluorescence lines which are at somewhat lower in energy. So the energy you need is actually optimized by the sample you study. And you can get that at a synchrotron. You can choose it. You can choose what energy you use. The intensity is the important thing. So there's a difference between energy and intensity. The intensity is how much is the signal, how many photons, how many X-rays come out. And there we could actually use, we could not use more intense X-rays. We are currently limited by the detector which we have. In fact, in many cases, we have to tone down. We have so many, our X-ray signal is so powerful that we have to tone down a little bit the incident flux which we have of photons. But in the ideal world, if you had a really good detector, like $1 million detector, which in principle is affordable but doesn't really commercially exist at this point, you could improve the sensitivity and enhance the image quality by that. And we also still have about a factor of 10 or 100 which we could crank up in the X-ray intensity. And so there is no other source, there is no commercially available X-ray source which gives you that flexibility in terms of energy range, but also in terms of intensity. And there's one aspect which I didn't mention in my talk is synchrotron X-rays are polarized. That means if you put your detector at a 90-degree angle, like you're polarizing sunglasses, they reject all the scattering, and that means you can handle much larger beams. You only get the fluorescence. The fluorescence doesn't follow the polarization. And with the commercial X-ray, you never have the X-rays polarized. And so wherever you put your detector, even if you had a very powerful commercial X-ray tube, which don't exist to that level, you would get a poorer image quality. But so in summary, we are not quite yet at the full optimization of the techniques in terms of sensitivity and image quality.
Hi, I was wondering if any additional information has been gleaned from combining the X-ray results to the original fossil? Has any new information from the original fossil been able to be gleaned in terms of additional structure or anything that's come out of the X-ray?
So, so basically, in terms of, at this point where we stand with the Thermopolis Archaeopteryx, in terms of the anatomy, let's say seeing something which hasn't been found in any of the Archaeopteryx specimens, that would have been very unlikely. And that was not the case in this particular study. So the main results, if you compare, I mean, this is the very first study ever done on an Archaeopteryx with this particular technique. So we cannot really compare it to the other samples. But now we have our second one. We just have done that. So we now finally have start to have a baseline. But in terms of the significance actually of the finding, it is really the fact that we have original material still conserved in the fossil. And that means there's a lot of hope. And there's also care in a sense. You realize that you have to be careful of how you treat this fossil. There's a lot of hope that soft tissue in general, and you will see when our next paper comes out on the Sanctus, that soft tissue which is not known or not visible in the fossils will be brought out. So it is really kind of certainly in terms of the evolution or the anatomy, it's not a breakthrough, but in terms of having knowing now what is preserved in the fossil right after all this time, we think we have a very powerful new tool, analytical tool.
All right, let's ask two more questions. We start with one in the back here.
And then this.
Yes, definitely.
Yes. Is there going to be an opportunity to apply this technique to examining the feathered dinosaurs of China?
Well, thank you for this question. So as I pointed out, the lining bird, we were able to get that. We haven't yet been able to get one of the feathered dinosaurs, but we are really working. I know that my colleagues are working hard to get one, and if you know someone who has one, let us know.
Could you use the technology that you used to get all the elements on the Archaeopteryx? Could you use that on the skin of other dinosaurs that didn't have feathers?
Yes. So what I showed you this first image of the T-Rex, and we have actually quite a series of dinosaur skin samples, and we compare that. We have even some reptilian skin samples. We even took, believe it or not, we got the skull of a turtle, and we got all kinds of things of still living organisms and those who are not fossilized yet, and we have put those already in the beam. So we're building up our library. We're building up our library of chemical elements as reference, and we are working on the dinosaur skin. So a little bit patience. There will be some publications coming out on that one.
All right, well, thank you for your questions, and let's thank Uwe again. And I suspect if you still have questions that weren't answered, Uwe would probably be willing to hang around for a couple minutes and answer them. So enjoy the rest of your evening. Thank you for visiting SLAC.